Award from COPSS in 2007. He's the author of an award-winning book, Struck by Lightning. Actually, a best-selling book, Struck by Lightning: The Curious World of Probability. Two other books in probability. The title of his talk today is Optimizing and Adapting the Metropolis Algorithm.
Okay. Thank you very much. Welcome, everyone. Thanks to the organizers for inviting me. I'm going to talk about the Metropolis algorithm, which is an MCMC, or a Markov chain Monte Carlo algorithm. And I come from a bit of a different community than most of the people at the conference here. So I'll try to explain the sort of things we think about with Markov chain Monte Carlo algorithms and the theory side. And hopefully it'll work okay. I'll use some simple examples, and hopefully it'll be a good way for us to sort of meet the communities. And if it doesn't work out, then you should blame the organizers for having invited me, because it was their idea, right? But anyway, we'll see how we do. So I'll start with just sort of the motivation. And so the motivation for Markov chain Monte Carlo really comes more from the applied communities. It originated in the physics community, but now it's very popular within statistics, which is more my community. And there's actually lots and lots of people, like thousands and thousands of different research labs out there, which are running these Markov chain Monte Carlo algorithms to try to sample from distributions. Many of them don't know much about Markov chains or anything about, let's say, a probability, really, or mathematics, but they use these from an applied point of view. So from those of us working on the theory of MCMC, is to say, well, what can we do from the probability side that can hopefully help or influence the way people use these algorithms? So the motivation for what most of the applied users would be is they would have, let's say, a Bayesian posterior distribution. So some sort of a big complicated density, which I'll always call pi here. Let's see if this works. So pi will always be what we call the target density. And it's supposed to be some density which is probably on a high dimensional space, and it's probably kind of complicated, at least in the sense of kind of messy, with lots of factors and so on. And we just have to believe that the applied users are telling us that this pi is the most important density in the whole world. And if we can understand pi, then that would be wonderful. And so our goal is to say, how can we understand this big complicated density pi? And what they'll want to do, they'll say, well, we just want to use this density pi, and we want to compute things like a probability, that is an integral of pi over some region, or an expected value of some functional h with respect to pi. So h would be a function from the high dimensional space into the reals, let's say. And these are sort of simple things. And of course, we all know how to compute probabilities and expectations with respect to a density. So you think, well, if it's simple enough, we can use calculus. If it's kind of messy, maybe we use numerical integration. But the reason this is not such a trivial subject is because usually it's high enough dimensional and it's complicated enough that we can't use simple calculus or simple numerical integration. So I'll just say sort of a typical pi, the kind of thing that the applied MCMC users from the Bayesian statistics community might use. Just to give an idea, I'm only going to say this for one slide. It's not the point of this talk. But here's a sort of typical thing they might have. So it might be a function of a bunch of parameters. So here, let's say k is equal to 19. So it's a 22-dimensional function. And it's just some sort of messy product of the different factors and different things. This comes from some normal distributions with parameters that depend on the other coordinates and so on. And it's just some sort of messy function. From a mathematical point of view, there's nothing too hard about it. It's a nice continuous function. It should have a nice integral and so on. But from a computational point of view, probably it's too hard to use your old tricks from calculus or even to do numerical integration if the dimension's high enough. Now, some of you are so smart, maybe you can do this one yourselves, but then imagine a harder one, right? Because you can always imagine a higher dimensional and a messier one with maybe hundreds of coordinates. And at some point, you can't do it by standard tricks. And so it's high dimensional, it's complicated, so what to do? And of course, the basic approach is Monte Carlo, which I'm sure we're all familiar with. And that's the idea that if we could somehow sample from this distribution, that is, write a computer program which generates these random high dimensional vectors which are independent and each have the right probabilities according to the density, well, if we can do that, then of course we can estimate, say, the expected value of a functional just by averaging the functional values over the sample. So that's sort of an old trick, I guess, from at least the 1950s or earlier. And so that works quite well. But the problem is, this first step is we need to generate random variables which have probabilities according to that density pi. And if pi is some sort of a high-dimensional messy density like the one that I mentioned, then not only can we not do it by calculus or by numerical integration, but also we don't know how to write a computer program which generates a vector which has probabilities according to that density. So instead, everyone, meaning thousands and thousands of research labs, use Markov chain Monte Carlo. And that's, again, what I think probably most of you do know, but since it's more for my community than yours, I'll review it. And so it's the idea, well, the basic idea is instead of coming up with an IID sample, because we don't know how to write a computer program to do that, we write a computer program to run a Markov chain which has pi as a stationary distribution. So it's just random iterations starting from some initial value and then iteratively running according to some algorithm or some Markov chain transition probabilities, such that, well, the hope is that for large n, the probabilities associated with xn are approximately pi, because we have a Markov chain which has pi as its stationary distribution and which is irreducible and aperiodic and so on, so that the probabilities should indeed converge as n goes to infinity to pi. So if you haven't seen this before, you might think a few things. Well, first you might think this isn't as good as ordinary Monte Carlo, because now these probabilities aren't exactly pi, they're just approximately so. Furthermore, the sample is no longer independent. We're getting a correlated sample. And that's true. It's not as good as ordinary Monte Carlo, but it's often the best that we can do. But you also might think, if it was so hard, to estimate the probabilities directly, or to do calculus or numerical integration, or to do ordinary Monte Carlo, how could it be easier to run a Markov chain? And if you haven't seen it before, that's sort of the strangest thing about the subject, is that it turns out to be way easier to run a Markov chain that has the right stationary distribution than it is to do anything clever about the distribution itself. And so the point is, if you can run a Markov chain like that, then you can still hope to get estimates which are of the form of averaging up the values of the samples. Not as good because it's just approximate and because they're correlated, but it's not too bad. And usually we'll throw away an initial number b of them, like the burn-in period, the initial phase, and hope to go to the asymptotic phase, and that works pretty well. But again, the question is, how do we really define? Why is it so easy to define a Markov chain, which is nice and simple, so we can run it on a computer, and yet pi itself was so complicated that we didn't know very much about it? And the answer is there's some very simple algorithms, and the most common and perhaps simplest is called the Metropolis algorithm, and that's what I'll focus on today. And again, it's something I think probably most of you know, but I'll just quickly review that the Metropolis algorithm is this very famous algorithm being used by thousands of researchers who don't know anything about Markov chains, and here's the Metropolis algorithm. So again, to sort of review, we have some target density pi, and that's this thing that for some reason it's the most important density in the whole wide world, but it's so complicated that we can't integrate it, and it's so high dimensional we can't do numerical integration, and we'd like to sample from it so we can estimate things about it. That's review. And so here's a nice simple algorithm. It's an iterative way to define the Markov chain x0, x1, x2, and so on. And it says once you have, say, x0, or once you have xn minus 1, then define a new value, which is the proposal value. And so I'll stick to the symmetric case. There's also an asymmetric case. But what we'll do is this is actually called the random walk Metropolis algorithm, so it's a special case. But take our old value, add some new independent randomness, just like a normal distribution or a uniform distribution or whatever, which is independent of everything else. And for now, let's assume it's symmetric. So you just add some symmetric increment and call that yn, and that's your proposal. So you're saying maybe we want the new x value to be our old x value plus this random increment. And then the Metropolis step is that you either accept or reject it. So there's a certain probability here. It's the minimum of 1 and the ratio of pi at the new value divided by pi at the old value. And with that probability, you accept it. So your new x value is indeed equal to y, the y proposal value. Otherwise, you reject it, and your new value is the same as the value that you started with. So very simple algorithm. We propose a new increment, and then we either accept or reject it. And you might say, well, is it feasible to run this? Because pi was this big, complicated, high-dimensional thing. But you'll see that all we need to do is compute the value of the density pi at a point, right? At the new point and the old point. And if you imagine, if you think back to that crazy formula I wrote, it's some crazy product of whatevers, but it's not hard to compute it at an individual point. And furthermore, another nice thing is we only need the ratio of two values, which means we don't need the normalizing constants. And that's good, too, because for a crazy product like that, we don't even know what the normalizing constant is. But we don't need to worry about that. So anyway, a very simple algorithm where you propose a new value, then you either accept or reject it. And this probability is exactly chosen so that the resulting Markov chain will be reversible with respect to pi. So pi will be a stationary distribution. And so assuming something like irreducibility, then indeed the probabilities will, as n goes to infinity, converge to the ones that we want. And so it's incredibly simple. And because it's so simple, lots and lots of people are using it. And then we think, well, what can we say about it? So I'm going to start with a very simple example, if you'll forgive me. So this will be, instead of x being a high-dimensional state space r to the d, x will just consist of 6 points. And the increment distribution q will just be uniform minus 1, 1. That is, we either subtract 1 or add 1 as the new proposal. And if you'll allow me, I'm going to actually run a little simulation with a Java applet just to wake us all up, I guess, especially me. And okay, so here's a simple Java applet where we've got these 6 numbers, 1, 2, 3, 4, 5, 6. And the blue bars here represent pi, represent the target distribution that's the most important distribution in the whole world, let's pretend. And so you can see these bars, the height of the bars adds up to 1, and it's some simple probability distribution on 6 points. The black dot represents the Markov chain. And I happen to start at the point 5 on the state space 1, 2, 3, 4, 5, 6. And then I'm going to propose to either subtract 1 or add 1 to 5. And so the computer is going to randomly choose uniformly one of those two things. It chose to propose to add 1, so it proposed to move from 5 to 6. Now the Metropolis algorithm has to decide whether to accept or reject that proposal. And it looks at the ratio of pi of the new value divided by pi of the old value. In this case, the new value has a larger pi, so it always accepts. So it means that this is going to turn green, and that means it accepted it, and it moves the black dot to the new value, and then begins again. Let me run this for a few iterations. So this time it's going to again propose either to add or subtract 1. OK, this time it proposed to subtract 1 to move from 6 to 5. Now it has a decision because it looks at the ratio of this height divided by this height. Looks like it's about equal to 3/4 or so. So with probability 3/4, it's going to accept this move. Otherwise, it's going to reject it. And I don't know what's going to happen, but OK, it rejected it. That's red. So that means the black dot stayed where it is. I'll get that running. And then it does it again. Oh, this time it proposed something outside the space, so it always rejects that. It didn't move. This time it's going to try again. OK, this time it accepted that, so it moved back. So the point is it's a simple iterative algorithm that moves around. And we'll get it running a little faster, keep things exciting so nobody falls asleep. So it's proposing to accept or reject. In fact, it's having a lot of trouble because it's staying at 6 and rejecting a lot. And let me add one more ingredient, which is the empirical distribution. So these black bars, the height of them represents the fraction of the time that this Markov chain, this black dot, has spent at each of the states up to this point. So we can see it spent most of its time at 6, but quite a bit at 4 and 5, a little bit at 3. It hasn't even made it to 1 or 2 yet. And this goes along, and maybe I'll get it going faster now that we've all got the algorithm, because it's just a simple illustrative example. But the point is, if you're running MCMC and you really care about those blue bars, but you can't figure them out directly, and you're running this black dot, this Markov chain, to try to understand the blue bars, then what you hope will happen is that over time, well, you can probably say the black bars will converge in height to the blue bars, right? That is, the fraction of time it's spending at the different states should eventually converge to the stationary distribution, which is the blue bars. And you can see it kind of takes a while, right? We've done about 150 iterations so far, and it's not great. It's only spent a little bit of the time at 2. Now we can make it go even faster, and let's do that to try to convince ourselves that over time, OK, it's getting close. It's still not doing too well at the state 1. But over time, it's hopefully getting pretty close. And in fact, we can prove that asymptotically, the black bars will indeed converge to the blue bars. But if you're running this from a practical point of view, your most important question is, how quickly will this happen? That is, you just want to run the Markov chain for a while and then use that to draw conclusions, right? And the blue bars could be a Bayesian inference problem about a medical study, and you need to know the probabilities that the drug's going to make people better and so on, and you don't want to get it wrong. So then you say, well, what can we do? So let me stop this for a second, and let me say, maybe I'll start again. And so what I want to talk about now is the issues of, OK, this is how we run the Metropolis algorithm. But we have a lot of choices in how we run it. And in particular, for example, let me change it a little bit so that now I've changed a certain parameter to 2. So now instead of just always proposing to add 1 and subtract 1, it's going to propose to either add 1 or add 2 or subtract 1 or subtract 2 with uniform probability. And of course, we can again run the Markov chain. I'll get it running maybe a little faster. And it's again going to propose. And then you say, OK, once again, it's still a symmetric proposal distribution. It's still going to converge asymptotically to the stationary distribution. Then you say, well, how fast is this one going to converge? Is it smarter or stupider to run it with this plus or minus 1 or 2 than to run it just with plus or minus 1? And of course, once you say plus or minus 1 or 2, why not increase it further, right? So let's go up to, let's say, plus or minus 1, 2, 3, or 4. Now it can propose sometimes to take bigger jumps, and it will sometimes accept them and sometimes reject them. Sometimes, of course, it will propose things way out here, and then it will always reject them. Then you say, well, maybe that's the smarter Markov chain, right? Maybe that's the best way to do MCMC for this simple example. Well, if you take that to the extremes, let me see if I can get this to work to go to. So I've now set it so it's going to propose each time plus or minus 1, 2, 3, 4, 5, 6, up to 50. Okay? So it's going to usually propose great big jumps right off the screen. Well, this isn't so good either, right? Because obviously now it's going to usually propose things which are off the screen. So in this case, the target probability is 0. For a more realistic case, it might have tails, but still the probability would be very small, so it would usually reject. So that's not so smart either. So then you say, well, what is it that we want to be able to do as far as making a smart algorithm? So that's a bit of an introduction to the Metropolis algorithm, and also sort of to the issue, one of the issues I want to talk about, because we say, okay, this Markov chain, yes, it does work. It converges asymptotically. The black bars converge to the blue bars, right? This Markov chain works well. But then you say, well, again, as I said, what if it's uniform on -2, -1, 1, 2, or for any gamma on plus or minus 1 all the way up to gamma? Which one's the best? So even though this is a very simple problem, it's still not entirely obvious what's the best choice of gamma. But in this problem, you can kind of eyeball it. But one thing we can say right away is that a smart choice of gamma is probably sort of in between the two extremes. That is, if we only propose plus or minus 1, that's not very efficient because we'll usually accept our moves, but we won't move very far. But if we propose plus or minus 50, that's not very good because we'll usually reject that. So we want something in between the two extremes. And if you think in terms of the acceptance rate, that is, what fraction of the time will these proposals be accepted in that Metropolis step, it shouldn't be too close to 0, because that means we're proposing things that we hardly ever accept. But it shouldn't be too close to 1 either, because that means we're not being very ambitious. We're probably just moving a little bit each time. So I just call that the Goldilocks principle, right? Not too hot, not too cold, not too big, not too small. So okay, so we've got this principle that's sort of the first thing you could say that theory can tell us is that we don't want the proposals to be too big or too small. But then you say, well, what else can we say? And so first of all, let's just do a similar thing, but on a continuous example, because most of the statistics examples are on a continuous state space. It's still discrete time, but continuous state space. And so here are 3 different runs where it's still a very simple example because the target is just a standard normal distribution. And the proposal is going to be a normal increment now with mean 0, so it's symmetric increment, but some sigma squared. And you say, well, what's a smart choice of the proposal variance? And here's 3 tries. So in each case, the red graph, that's the target distribution. And then with time going upwards, here's our run of the Markov chain. So here's the first one. It runs around. And you can see it's not very efficient because it really takes a long time to move anywhere. And we're going to have to run it for a long time before we've got accurate estimates using this Markov chain. And this is a case where the proposal was too small. Here's a case where it, again, isn't very good. And I don't know if you can see too well, but if you look closely, you'll see there's regions where it sort of stays constant for a long time. And this is a case where it's proposing things that are too big. It's getting stuck a lot. So it's like in the previous example where gamma was 50 and we were proposing things that were too big. That's not so good either. Here's a sigma in between, which is much better. And here you can see that the Markov chain, I mean, they all have the same stationary distribution, but it's converging much more efficiently. And if we run this to try to estimate expected values, we'll get a much better answer much faster using this chain than either of those two. If you think in terms of the acceptance rates, AR for acceptance rate, then here, because the proposals were so small, the acceptance rate was 96%. We almost always accepted these little moves, but it wasn't very good because the moves didn't take us anywhere. Here, the acceptance rate was 5%, so we hardly ever accepted these moves, and that's why it's very choppy. We're not really going anywhere. In this case, the acceptance rate, well, was equal to 44%, which is somewhere nicely in between the extremes, and this is actually, in some sense, the best choice in this case to really explore well. So we propose things big enough that if we accept them, it's good, but small enough that we'll accept them with a reasonable probability. So we have this kind of balancing act going on. And then you say, well, OK, so these simple one-dimensional examples are pretty easy, but what if we had a higher dimensional example? Well, in this case, we'd be proposing things which, let's say, move in all the coordinates at once. Well, it's going to be harder to accept because if you think about it, if any coordinate goes too far away, it's probably going to be a small target value, and it's not going to accept. So we probably are going to want smaller proposals, but how do we figure that out? And how do we make some progress from the theory point of view? So well, one nice trick is to consider diffusion limits, which I'm sure this audience knows an awful lot about, more than I do. But so the basic idea, so I'm sure we all remember the sort of analogy that if you take just a simple symmetric random walk, so it adds or subtracts 1 with probability a half each, but then you speed up time, so you're adding and subtracting faster and faster, but you shrink down space by order of the square root of the amount you sped up time, then you'll converge to Brownian motion, right? You'll converge to something which takes lots and lots of little steps, and there's sort of this diffusion limit going on. And so there's an idea, and this actually predates me. It goes back to Gareth Roberts, who's here, and his co-authors from 1994. And it says, let's look at a random walk Metropolis algorithm of the type that we said. And in a high dimension D, we're going to take the limit as the dimension goes to infinity, which is sort of a way to think about the theory, and take the proposal distributions which have an increment, which have, the mean is 0, and the variance is, let's say, some L squared. Well, we'll normalize it as L squared over D times the identity. And we'll say, well, what's a smart choice of L? That is, how should we scale these proposals? And what they proved is that if you take the following thing, so look at the first coordinate first of all, so we get a one-dimensional thing that we can think about better. Speed up time by a factor of d, just like you did for Brownian motion. Shrink space by a factor of the square root of d, just like you do for Brownian motion. Then for certain pi, and I'll say more about that later, but under some fairly strong assumptions, you again get a diffusion limit. And you might say, well, that's great, I love diffusions, right? So that's good. But you might also say, how is that going to help us to understand Markov chain Monte Carlo algorithms? Those applied people in those labs, they don't want to hear about diffusion limits, right? I can assure you that. So we say, well, how could this help us with them? Well, the point is, actually, the nature of this limiting diffusion tells us a lot. So here's a slide with a little more detail, but nothing too really to worry about. It's just saying, well, first of all, this same thing I said, this first coordinate sped up by a factor d and shrunk in space by a factor square root of d, converges to what's actually a Langevin diffusion, which has the correct stationary distribution, as it turns out. And never mind that, because that's a horrible, ugly equation for me, maybe not for some of you. But in particular, it has a speed function, and it depends on L. So remember just a second that L was related to the proposals that we did. So in terms of the choice of how big a proposal you did, you get a speed, which is some function of L. And it's some messy function. Never mind that. This is the CDF of a standard normal, but some messy function for the speed. Also, you can compute the asymptotic acceptance rate. That is, if you run this algorithm and then you let the dimension go to infinity, what will the acceptance rate be? What fraction of time will those proposals be accepted? That you can get another explicit messy function. And so then you say, OK, well, in this limit, we understand the speed of the limiting diffusion. And we also understand the acceptance rate. And then you say, well, now let's get back to the question we wanted to optimize, right? We wanted to say, what's the smartest choice of L? Well, in terms of this limiting diffusion, the smartest choice of L will be the one that leads to the fastest version of the diffusion, right? That maximizes the speed. So we can say that there's lots to learn here. And in particular, this speed is an explicit function, and we want to maximize it. And it turns out that you can maximize it easily numerically. This constant still depends on the target, but in a way that we understand. But you say, OK, this optimal value of L, which was related to the proposal scaling, can actually be calculated in an explicit way. And then we can compute the corresponding acceptance rate corresponding to that smartest best choice of L. And the most amazing thing is that at least for this certain class of targets under certain conditions that I'll talk about, the optimal acceptance rate, or the acceptance rate corresponding to the optimal choice of L to lead to the fastest limiting diffusion, is actually just a number, so 0.234. Somehow a number that's independent of the precise details of the target distribution. And so we already knew, well, we probably want the acceptance rate to be far away from 0 and far away from 1. Now we're saying, yeah, but more precisely, we want it to be 0.234. Right? So it's this sort of amazing result, even though it's under quite limited circumstances. And well, so this just kind of repeats it. So it's optimal to choose this proposal, to choose sigma with this optimal L, which leads to an acceptance rate of 0.234. And as you can imagine from the applied community's point of view, they don't want to know about the limiting diffusions, or they don't want to know about any of this stuff, but they love numbers like 0.234, right? Because you can do that on your computer. So this is a nice result, which I can say, because again, it predates me, but it started part of the subject, and it says, hey, here's a really useful piece of information that we can tell to the applied community. Let me say briefly, so there's these conditions on pi, which are actually pretty severe. And the original proof from 1994, it assumed that the target distribution pi could be written as a product of sort of the same density function separately in each of the coordinates. So it's sort of like each of the coordinates in the d-dimensional target were IID, which is, of course, a very artificial assumption, and you would never need to use MCMC in that case. And as long as f was smooth and had various moments and so on, then that would suffice. There were some generalizations of that. One I'll mention is my student Mylène Bédard did some generalizations where it's still product form, but you got different scalings in the different dimensions, so it's a somewhat more sophisticated case. There's been some other generalizations by Gareth and his co-authors recently too. But it's pretty restrictive. But what's also neat is that when we try it out in applications, it seems like for a lot of targets, 0.234 is at least pretty close to optimal, even in targets which don't at all satisfy these artificial assumptions. So anyway, so we say, OK, well, now, boy, are we smart, because we know the optimal acceptance rate, and even though we've only proved it in a certain setting, we think it's approximately right in other settings. It's useful information to tell the practitioners. Then you say, well, is that really everything? Because after all, we had sort of a high-dimensional problem, and our algorithm is a high-dimensional algorithm with these proposal distributions in high dimensions. And are we really going to reduce everything to a single number, right, as long as the acceptance rate is 0.234? That doesn't sound right. And here's another example to illustrate that. Still a very simple example. Still the target is still going to be a normal distribution. But now in higher dimensions, so let's do it in dimension 20. And sigma is just actually something I generated randomly, so it's not, it doesn't have any kind of nice structure to it. And then we say, okay, so we've got some, high dimensional, or at least a little bit high dimensional target distribution, and we'd like to run a random walk Metropolis algorithm, and we think we're so smart because we know 0.234 is the optimal acceptance rate, and let's see how we do. So this is a graph of just the first coordinate, and here's our first try where we said, okay, let's let that proposal increment distribution just be a standard normal in 20 dimensions. And we see, well, it doesn't work that well, right? Here's the thing in the first coordinate of what we were trying to converge to, and we just kind of got stuck. But then we say, well, look, the acceptance rate was 0.006, much too small. So that means our proposals were too big, right? Like when gamma was 50 in that first example. So the proposals are too big, and if we try to estimate something like the let's say the second moment of the first coordinate, which should be 24.5, it's not even close. So this is bad, but we say no problem because we used a proposal variance that was too big. So we say, okay, let's try a smaller one. So here's our excuse me, here's our second try where we use a really, really tiny proposal variance. And we say, well, that one stunk too, right? Because it barely moved at all. But then we say, well, that's not so surprising because now the acceptance rate was too high, right? It was 89%. So now we're using a proposal that's too small. We need to be more ambitious. We need to take bigger steps. And again, the expected values are way off. So here's a third try. Here's where, I tuned around for a while and I found out that this multiple, this proposal scaling, now we get the acceptance rate just about equal to 0.234, which we thought we were so smart about. And it's still not good, right? It's a little better maybe, but it's not really moving that efficiently. Pardon me? So this is just for 1,000 samples, and it is a good question. I mean, you could say maybe 1,000 samples isn't enough and we need to run it farther. But you can also say, this wasn't that hard a problem, and if after 1,000 samples we're doing that badly, surely this isn't the best we can do. And so, but I mean, you could say, well, it's high dimensional, so maybe it's hard to get it to work. But then you can say, well, maybe there's something smarter. And here's a fourth try, where now the proposal is again normal, again symmetric, centered at 0, the increments. But this time it's some constant times not the identity covariance matrix, but sigma, which is the target covariance matrix. And the acceptance rate is pretty close to 0.234. I didn't even bother getting it exactly right. But you can see this works much better, right? Even with 1,000 iterations, as Sean says, it's doing pretty well. Now, you could still argue if this is optimal and if there's ways to fix it up, but it's much better and we're getting pretty good expected values. And then you can say, okay, if we ran it for more than 1,000, we get even better answers. So you think this is a smart thing to do. So you say, well, maybe that's interesting. So maybe it's not enough to get the acceptance rate to be about what we think is optimal, but also we need the shape of the proposals to be smart, and in this case, to approximately imitate the shape of the target. And indeed, that's true. So here's a theorem which says that, again, under certain conditions on pi, which are similar to the original conditions, but then we can take orthogonal transformations and so on. But again, certain conditions which are fairly restrictive. We can say if you're doing a random walk Metropolis with Gaussian proposal distribution, then indeed, the optimal thing to do is to use increments which have an increment which is where the covariance is actually proportional to the target covariance. And it's still optimal to get the acceptance rate asymptotically to be this magic 0.234. So that part was right, but that wasn't enough. We also needed to get the shape right, too. And we saw in that example that can make a big difference. But the more alert among you might, well, first of all, again, even though we only proved it for certain cases, it actually seems to approximately work in other cases, too. So we think this is pretty good. But the more alert among you will say, well, now we're using sigma, right, which is the covariance of the target distribution pi. And remember, a typical pi is something like that thing I showed you back on the second slide with this big messy product, and we already said it's too hard to integrate and so on. So it's too hard to compute the covariance, right? How can we compute the covariance of this big messy high dimensional density? So if we happen for some reason to know sigma, then this would be a smart thing to do. Usually we don't. So then you say, well, maybe this is kind of useless, but it wouldn't be the first time I've been told that about my work, actually. But anyway, you say, OK, maybe this is kind of useless. But then you say, maybe there's something else we can do that's smart. So what if sigma is unknown? How can we still make use of what we kind of know is the optimal or the smart way to do this Metropolis algorithm, but it uses something that's unknown? And so another idea is to use what's called adaptive MCMC, which is an idea pretty much introduced by some Finnish authors in about the year 2001. And I know people have used adaptive in various ways in some of the previous talks, but what we'll mean by adaptive is that we're running a Markov chain, but then we're going to cheat. So we're going to run a Markov chain, but we're going to learn things from the previous history as we go. and we're going to modify our algorithm, in this case our proposal distribution, as we go. And that's the sort of thing that, in general, you can't do, right? If you want to run a Markov chain, you have to let it run. You can't learn things from the history, or it's no longer Markovian. But anyway, so here's how we'll use it in this case. We'll say, if we knew sigma, remember, that was the covariance of the target distribution, and we've convinced ourselves that if we knew that, then we'd be really smart and we'd run a really good algorithm. But we don't know that. But what we do know easily is the empirical estimator of the covariance, which we'll call sigma n. That is to say, once we've run the chain for some amount of time, let's say the first 100 iterations, then we say, OK, we've got 100 points. They're not really a sample from pi, but we could pretend they're a sample from pi. And then we could say, if this is a sample from pi, then what's the corresponding covariance? And that's something that we can estimate. We do that in statistics all the time, estimate a covariance matrix based on the data that we get. So there's a simple formula for that. So we can estimate the true target covariance matrix sigma by this sigma n. And if we do that, well, then we can say that for large n at least, hopefully if our samples were kind of OK, then maybe sigma n is kind of like the sigma that we really wanted to use. And if it is, then this what we really want is this really smart proposal increment for the Metropolis algorithm. But we could approximate it by just sticking in the empirical estimator. And if that worked well, maybe we can use this proposal instead. And maybe we'll sort of learn about a smarter algorithm as we go. You can say, well, are we allowed to do this? And the short answer is no, right? I mean, when somebody's going to run a Markov chain algorithm, the only reason pi is the right stationary distribution is because it's reversible and because you run it consistently and not because you cheat based on the history. But it's true. Sorry, I don't mean to sound emotional or anything. But anyway, but then on the other hand, well, first of all, I'll say an example that worked well, as I'll show you in a second. But sometimes it can be a disaster too. So I'll show you two cases, one where it works really well, one where it's a disaster, and then I'll talk a little bit about some theory for when it works and when it doesn't. So first of all, here's an example where it works well. And this looks a bit like there's a tornado coming to town, but it's not that. It's just, so this is the time is going up now. And this is the first coordinate of a 200-dimensional example, again, just a test example, where so the true target in the first coordinate is something like this. And we can see that from about here on, this is actually a sampler that's working excellently. It's mixing well. It's exploring the space. It's converting well. The covariances are small. I should say the autocovariances are small of the chain. So this is a great Markov chain, and we're all really happy. This is a terrible Markov chain. This is a Markov chain which is trying to sample from something which is about this wide, and it's only finding this little bit of it in the middle because it's kind of like those earlier pictures where it's using a terrible proposal increment covariance, and it's not converging well at all. And you might say, well, that's OK. It only took, what, maybe like a few centimeters, right? But this is actually 1 million iterations here. So you can see there's 1 million iterations and 2 million and 3 million. So roughly speaking, it takes about 1 million iterations until it becomes smart. And starting after 1 million iterations, fabulous Markov chain, great estimates and everything. For the first, say, 500,000 or so, terrible, and you would indeed get the wrong answer if you use it. But what's the point of this? The point is this is learning as it goes, right? So it's starting by just running and getting some initial samples and using those to estimate the target covariance, getting a terrible estimate for the target covariance because it's 200-dimensional, which is a hard thing to estimate, a 200 by 200 matrix. And therefore running a bad algorithm, not converting well at all, finally learning. So from our point of view, we say, OK, adaptive MCMC, yes, you have to wait a while. But that's OK, right? Because computers are fast, and we can go do something else while it's running. And we have to wait a while, but then we get a really great sampler. So we think, overall, this is a good argument for, yeah, it's smart to do this adaptive stuff. Because this kind of tuning in 200 dimensions, we could never have done it by hand, right? We couldn't have eyeballed a 200-dimensional covariance matrix, right? So we couldn't do it by hand, but the computer can help us, and we can run a great chain eventually, as long as we let it run long enough. But on the other hand, let me, before I go to that, I'm going to run another simulation for you, a brief one here. So this is a simple example of adaptation to show you that you can't just be glib when you run an adaptive algorithm. So we'll go back to my favorite state space, which is 6 points that you're all familiar with. I'll start with actually the uniform target distribution, but then I'll change it in a minute. And let me run this so it will adapt. And what I'm going to do is I'm going to run an adaptive algorithm. So the logic now is, remember before we said it's not clear when you start this whether the gamma, that is how big a proposal you're allowed to do, should be just 1. Well, that's a bit too small. But if it's 50, well, that's way too big. Now, you can really eyeball it and say, OK, it should be about equal to 4, let's say. But suppose you say we couldn't because it was a high-dimensional example. Can we let the computer do it for us? So here's one way we could do adaptation. We could say, what I'm going to do is I'm going to run one step of the Metropolis algorithm, and then I'm going to see whether we accept or reject that move. That's part of the algorithm. And then, well, if we accept it, then the logic will be, well, maybe we're not being ambitious enough, right? It's sort of easy to accept. So we'll add 1 to that parameter gamma. We'll say, let's make a bigger thing. Whereas if we reject it, then we say, OK, maybe it's like when gamma is 50 and we're proposing things that are too big. So then we'll subtract 1, at least down to a minimum of 1. So let's see if this works. So OK, we propose, I guess it started with gamma as 2. So the first time it's going to run what we've seen before, plus or minus 1 or plus or minus 2. OK, it chose -1, and it's going to accept that. But now it says, OK, I accepted a proposal. Maybe I'm not being ambitious enough. Maybe I can make it bigger. So this time it'll do plus or minus 3. I didn't change it. That happens automatically. I'll get it running. And this time it accepted again. So it says, OK, let's do plus or minus 4 now as our next step. And OK, that time it rejected. It says, OK, I'm getting a little too big. Let's go back to plus or minus 3. That one it accepted. It'll go to plus or minus 4. I'll get that going a little faster. And so you can see, so it goes down. And the gamma values, which are how much spread there are, they get a little bigger and a little smaller. Let's run it even a little faster. And while I'm at it, I'll put in the empirical bars again. So it's again, and it's a little hard to see, but if you look at those white dots, you can see sometimes there's lots and lots of white dots because it's proposing big things. Sometimes there's only a few white dots because it's proposing small things. And it's not great or anything, but nonetheless, I didn't have to tell it that 50 is too big, and I didn't have to tell it that 1 is too small. It's kind of balancing out as it goes. In this case, the gammas, that width, it's not converging to anything, but it's sort of going back and forth between reasonable values. And you can see the gamma values there too if you want. Right now it's about 7 or 8, but sometimes we'll go to smaller values too. We'll go back to a slower speed. That's a little too fast. But anyway, so you can see it's going pretty well. And you might think, boy, isn't this adaptive Markov chain smart? Because by using a little bit of the past history, we find ways to get approximately the right width as we go. But on the other hand, as probably many of you will know, when you start messing with Markov chains, you have to be really careful, right? And let me change the example now. So it's still approximately uniform, except the point 2 now has just an extremely small blue dot you can maybe hardly see. And you say, well, I'm still going to run the same algorithm because I still think it's a smart algorithm. And let's let it run. And again, it starts with a certain gamma, and it goes to bigger gamma, and it goes to smaller gamma. And again, we think we're so clever because it's choosing the gamma for us. We don't have to choose it. But then after a while, and some of you maybe can already see there might be trouble. So let me run it faster for a while. And so far, it looks pretty good. And it's jumping around. And the black bars are not so far from the blue bars. And, aren't we clever? And let's see. I don't have too much time left, so I hope the trouble starts. At some point, randomly, some trouble will occur. And some of you may be able to see, well, OK, there it happened. So what happened now? It was jumping around. It happened to go to the point 1. Well, nothing wrong with that. And then it happened to reject a few times. Nothing wrong with that. But when it rejects, it makes the gamma value smaller. And at some point, gamma got down to 1. And now it's in a place where it can only propose to go to 0 or 2. If it proposes 0, it always rejects. If it proposes 2, it only accepts with probability given by this tiny dot over that thing. So it has a very small probability of accepting. So it's actually going to be stuck there for a really long time before it escapes. And in fact, you can see that the black bars are not converging to the blue bars at all. They're converging to the wrong thing. And so it's a bit of a subtle example, I think, even though it's just such a simple example, because when I first thought, I said, well, as long as at each step we're preserving the reversibility, how could it go so far wrong? But the answer is that it can, because what we do next depends on the whole history too. And this is a case where it's easy to get into this trap, because we can get into 1 by jumping over 2. But then once we're stuck in this trap, the only way to escape is by going through 2. So we've sort of broken the symmetry. And in fact, if you look at the pair process consisting of the x, the black dot, and gamma, this width, that's jointly a Markov chain in this case. And it does have a stationary distribution, but it's not at all the right one. And so the stationary distribution has a great big black bar here. So it's completely wrong. So the point of that, and I'll stop that now, is that when you do this adaptive MCMC, it works great sometimes. But we know that you can't just do willy-nilly adaptions, or you mess up the Markov structure, and you don't necessarily converge to the right thing. So here's, so we can say, is it valid to do these speed-ups? They seem to help us, but are they valid? And so here's one thing. I mean, there's a number of people who have worked on these adaptive algorithms, because again, from a practical point of view, they seem to help a lot. From a theory point of view, they seem to be highly questionable. So what can we say? And so this is something I did joint with Gareth, as a fair bit of this work was. I hope I've mentioned his name often enough. But anyway, so we said that adaptive MCMC, and not just this particular example of the adaptive Metropolis algorithm with the empirical estimators, but any adaptation which sort of uses the previous history, it will still converge asymptotically to pi, so at least it's valid, assuming a couple conditions. The first one is what we call diminishing adaptation. And this says, so this looks like a bit messy, but what it really is talking about the transitions corresponding to the random choice at time n, and comparing those to the transitions corresponding to the random choice at time n plus 1. So the Markov transition you use at time n compared to the Markov transition at time n plus 1, in other words, how much you're adapting or how much you're changing your proposals, that has to go to 0 as n goes to infinity, at least in probability, even in the soup here. So what that means is that it doesn't mean that you have to stop adapting a while, and it doesn't even mean that your adaptive parameters have to converge to anything. We don't require that. But it just means the amount of change from time n to n plus 1 has to go to 0. So that could be because, for example, the probability that you're going to make a change at time n, that goes to 0. Or you could be making changes, but things that go smaller and smaller. So that's our first thing. And this is violated for that example I just said, the Java applet example, right? Because there we're changing by 1 all the time. We don't have any diminishing adaptation. The second thing is more of a technical condition. It's what we call containment. And it says, as you run this adaptive algorithm, and then you look at where you are at some time n, call that xn, and your choice of the adaptive parameters at time n, the random thing, call that gamma n. If we then say, OK, we're going to start from that xn and fix that gamma n, and see what's the time to converge to stationarity starting from there, then that has to at least remain bounded in probability as n goes to infinity. It can't sort of squidge off to infinity. This is kind of a technical condition. If you have some sort of a compactness or some sort of a bounded problem, then it's pretty easy to verify this. If you don't, then it's harder, and it depends on if the tails of the target are sufficiently light and so on. So there's a little bit to worry about there. But for the most part, this condition is satisfied. And this first one, since we get to choose how we do the adaptation, we can just choose it to make sure that it's satisfied. So roughly speaking, we feel that it's not too hard to satisfy these. And for example, they're satisfied in that example I had with the tornado and the fact that after 1 million iterations, it learns. So roughly speaking, we think it's reasonable to do this. And then in applications, as I've already kind of said, sometimes adaptations really do make a lot of speed-ups, and even in problems in hundreds of dimensions. So I have some examples with Gareth, which are more sort of test examples, but then also recently in work with Sylvia Richardson and her postdoc. So those are serious application people who do statistical genetics problems with hundreds of dimensions and so on. And actually, they heard one of our talks and said, hey, we should be able to use this in our application, and they've just finished something now. Well, I guess we have their application in my theory, but to say that they could still, in hundreds of dimensions, find ways for their statistical genetics algorithm to modify the algorithm as it goes in a way which seems to be giving them good speed-ups too. So we're happy about that. So anyway, so we think adaptive MCMC is pretty interesting. Let me see. I know I'm just about out of time because we all want to go to lunch, and I'll spend 1 minute each on 2 other applications, and then I'll finish. So one is sorry. 8 minutes? Really? You're all having such a good time here. OK, well, I'll spend somewhere in between my 2 and his 8 minutes. How's that? So, OK, so anyway, another application is to simulated tempering, and this is more recent work. And so simulated tempering is another algorithm that I'm sure some of you know quite a bit about, but maybe not all. And okay. I guess since I have 8 minutes, I can take a drink of water. OK, so simulated tempering is this idea where you have a target distribution pi as usual, so it's still the MCMC context, and you'd like to sample from it. But typically, it's a multimodal thing. So there's just some big amount of pi over here, but then it gets small, and then some big amount over here. And if you run a typical MCMC, it's hard to get from this part to this part and so on, so you'll tend to get stuck. And the idea of simulated tempering, which is an old idea, is to sort of flatten out the distribution, replace it by a family of distributions which are raised to fractional powers. And of course, if you raise a density to a power that's in between 0 and 1, you tend to flatten it out. It all tends to get, all the values tend to get closer to 1, so it kind of flattens it out. And so that's something people do a lot, but then you say, well, these fractional powers, which are called the inverse temperatures, how should we choose those inverse temperatures? And that's something people talk about. And so yeah, we'd like to design them so the algorithm can move efficiently between these different inverse temperatures so it can use the benefit of the flatter distribution in order to hopefully learn more about the original distribution, which is what we want. And so one particular question, is just one part of the puzzle, is how do we choose these inverse temperatures beta I? And often they're chosen just by some sort of a power law, that is to be geometric. But we said, well, maybe there's a way to optimize that, to talk about how to optimize that choice. And under certain conditions, again, it's somewhat restrictive, but this is joint work with Gareth and also Yves Atchadé from the University of Michigan. And we said in, again, a certain limiting context, and there's assumptions and so on, that it's optimal to choose these betas so that whenever you propose to increase to the next inverse temperature, the probability of accepting it should be that same old magic 0.234. Right? So So somehow this 0.234, it sort of comes up in a lot of cases, and of course it comes up in the same way, but the details of the proof are different because we have sort of a different context. But again, we're taking the limit where we get into a diffusion limit and we talk about optimizing. So anyway, I won't say more about that. Let me say finally, Langevin algorithms, and this is something I worked on actually getting to be a while ago now with Gareth, and their cases, so far all the Metropolis algorithms that I've discussed are these random walk Metropolis where you do a symmetric increment distribution. But some people have proposed, well, maybe it's smarter, don't just do a symmetric where like we take our old x and add something symmetric like a normal, but we'd also add here something in the direction of the gradient of the target. So now usually in applications it would be a mess to compute the gradient of the target, so people don't usually do this. But in principle, if you knew the gradient of the target or if you could compute it, then you could say, well, you know, we know pi is getting bigger over there, so maybe it's smarter to propose things which go more in that direction. And then we said, well, is there a way to do the optimal scaling and so on in that case? And so this is something from a while ago now, but we said that in this case, it's a similar, although a harder diffusion limit because there's extra terms to bound or whatever, but roughly speaking, it's a similar limit. And you get a similar thing where, again, you need to scale, but instead of scaling sigma like d to the minus a half, it turns out you have to scale it as d to the minus a sixth. And you still get an optimal acceptance rate, but instead of 0.234, you get 0.574. So another universal constant somehow, again, under certain conditions, assuming a product formed for the target and so on. But still, we think, you know, kind of interesting. So it does prove that from a theory point of view, it is much more efficient to use the Langevin algorithm instead of the usual random walk algorithm, if you can do it. So far, people don't tend to do it, so it hasn't had, well, I shouldn't say entirely. There have been some people who've used it, but for the most part, it's not as popular as the random walk Metropolis, but still the theory has something to say. So let me just wrap up, and then we can go to lunch, and then we can listen to Gareth, and then we can watch the football, right? The important things. But okay, so just to summarize, first of all, you know, if you get nothing else from this talk, if you were not previously familiar with the Metropolis algorithm, I hope you'll learn or believe me that, you know, it's this really important algorithm that thousands and thousands of applied users are using, and that's why it makes it interesting for us to study. And this issue of sort of optimizing or improving or choosing the algorithm is an important issue. And you know, the simplest first thing you can say is your acceptance rate should probably be far from 0 and far from 1 if you're running a balanced random walk Metropolis algorithm. More precisely, we have various optimizations, things like this magic 0.234, or this thing about this is the best form of the target proposal covariance and so on. So we have these various theorems under certain contexts. We also have this idea that if you want to use unknown information, like the target covariance, you can use these adaptive algorithms. And sometimes the adaptive algorithms can be pretty smart, at least if you run them for a long time. And they can be valid if you satisfy certain, what we consider relatively simple conditions to make them valid. And it can, in practice, it can lead to tremendous speedup. So we feel this at least has the potential to be important for applications too. Well, first of all, here's my webpage with all my papers and applets and so on if you want to know more. And also, Jose asked me, well, you know, what does all this have to do with computing rare tail probabilities? And I said, I don't know. But just to spend my last 30 seconds on that, it is an interesting point because in principle, with all this MCMC, we're trying to sample from pi. Now, if you say, well, okay, I believe that pi is the posterior distribution, but what I really care about is some extreme tail event. You know, what's the probability that the financial loss is more than 1 million or whatever? Then, for the most part, just ordinary MCMC will not do very well for reasons that you all know much better than I do, because you'll hardly ever get those samples, and you'll have a good absolute error bound, but not a good relative error bound. Now, it is possible to use tricks like exponential tilting and so on to try to work on that. For the most part, people don't in MCMC, and I think part of the reason I was talking to Gareth is that usually in MCMC, you know, the models are not believed to be that good or that accurate that you really think you can get a good estimate of the probability out in the tails anyway. So it's a bit of a delicate point, but I think there's definitely something to be done there to combine MCMC ideas with some of these tail probability estimates that some of you are expert on. But anyway, I'll leave it there. Thank you very much.
Questions?
So when the adaptive MCMC is not working, from the diagnostics, it's easy to identify that it's not working. But if it's working, then the burn-in period is sort of, you have to decide, right? If you have a 200-dimensional chain, are there some diagnostics for deciding burn-in for each coordinates?
Yeah, it's a good issue, this, you know, how do you decide what's the initial burn-in, the transitory phase that you want to throw away? And even for ordinary MCMC, never mind doing the adaptation, that's already an issue because, you know, you start at just some point that you can start at, and it's probably not a very good sample, and you'd like to not count that. And I have done some work on trying to balance sort of the convergence rates just for ordinary MCMC to say how much do we have to throw away. And in some cases, for some reasonably complicated examples, we can actually get a quantitative bound on that, say, if you throw away 450 iterations, then you'll be within epsilon of stationary. But for the most part, that's pretty hard. And then with this adaptive stuff, there's a second layer of that, right, which I think is your question, because then you're saying, well, it's not only that there's too much influence from the initial distribution of the Markov chain, but also there's influence from the fact that the adaptation hasn't yet gotten me to a smart chain. And for the most part, we don't really have good thing. I mean, you can try to do sort of ad hoc diagnostics where you sort of look at the output from the chain and see if it appears to be stationary in a statistical, like in a time series kind of sense. And that's what people tend to do. It's not that accurate because it could be that you're stuck in one part of the space and it appears that you've reached stationarity, but you really haven't. So it involves some combination of, analyzing the output and some judgment and really some luck, because you could sometimes be tricked too. So that's a hard problem in MCMC, I guess. But
You generally do it coordinate-wise if you have a 200-dimensional chain, really. Then
well, you can try. I mean, of course, in a real example, the 200 dimensions would not be at all independent. So even if in one coordinate it seems like, okay, this is working okay, maybe it's not really balanced with some other coordinate too. So anyway, a lot of issues there, but discuss over lunch.
One follow-up to that. If you're looking at the adaptive MCMC, you can put it in the context of two-time scale stochastic approximation.
Right.
And you can pick up Vivek Borkar's book and get formulas of the asymptotic variance.
Right.
I mean, which is good, which you'll find pretty negative probably. One quick comment on page 21, I think. I can't resist. 20, yeah, there.
Here?
So, so if you don't have that term, then you've got a skip-free Markov chain, and you've got all the horrible problems I talked about in my talk yesterday. But if you put that term in, and if the acceptance rate doesn't go to 0 for large x, the Markov chain satisfy the Donskoy-Verdine condition. I mean, if log v is blowing up, and so that's that Markov chain doesn't have any of the pathologies I talked about in my talk yesterday. They're really general conditions.
Okay.
There's a lot of motivation for sticking that.
Okay.
You get a much better than exponential drift in the Markov chain. Very general conditions.
Right. I mean, I should emphasize that this is just the proposal, of course, then you still have the acceptance rejection. But I think you're taking that into account.
Acceptance became bounded from below it to large.
Yeah, I mean, it usually would. Like the asymptotic acceptance might be equal to 0.574 or something.
Well,
So
as long as it's non-zero, you'd have a discrete spectrum for the resulting Markov chain.
okay.
Instead of just a gap.
Okay. Interesting.
Oh yeah.
You defined the proposal distribution as additive, whereas the sort of traditional definition of Metropolis Hastings is a distribution defined on the whole target space. I presume that's because you're dealing with multidimensional cases, high-dimensional cases, where it would be difficult to sample from the target space.
Well, I mean, it's true that the most general form of the Metropolis Hastings algorithm, you just say starting from x, your proposal distribution is some q of x dy, let's say, so some proposal. And it's true that what we call the random walk Metropolis is sort of the special case where q of x dy takes on the form that it's centered at x with a symmetric increment. But in general, if it's not symmetric, then the same basic algorithm works as you're saying. You just you need to modify the acceptance probabilities to take into account also the ratio of the proposals. And I mean, it's true that in high dimensions, the more complicated thing you try, the harder it might be. But there could well be very smart versions of the Q which are not of the form random walk Metropolis.
Because not doing it additively would dodge a lot of the problems you had with endpoints or things like that.
Well, possibly. I mean, yeah, certainly. I mean, like one other extreme is what's called the independent sampler, where the proposal Q actually doesn't depend on X, the current point. You just propose according to some new distribution. And that's certainly a case which is kind of like what you're saying, that it's not that you're stuck in a bad spot so much because you're going to propose from some big thing anyway.
You
But
find a nice proposal distribution to start with.
yeah, you can try.
Adapt that.
Yeah, that's right. In fact, people do work on the so-called adaptive independent Metropolis. In fact, and Robert Cohn from Australia, some of you might know, who works on some of those things too. So that's right. So that's the case where you're trying to adapt a single proposal, which sort of is the same proposal no matter where you are. And it's true that the more you can make that proposal look like the target distribution, the more you'll accept that and the better off you'll be. So that's certainly another approach. Yeah. Okay, thanks.
You're good now.
About this, I read somewhere the phrase that MCMC is not only science, it's also an art. It's a mixture of science and art. I agree with this.
Well, that's true of all our subjects, isn't it? I mean, we all need an art, but
All the choices, you know.
yeah. Well, I guess it's true. I mean, I guess you could say that to the extent that we can prove an optimality, I guess that sounds more like science because we're saying this is the best way. To the extent that applied people in their labs are saying, well, we tried this one and it didn't work, but we tried this and it worked a little better and so on, maybe that sounds a bit more like an art. I guess people say for statistics in general that applied statistics is maybe more of an art than a science, so there's probably something to that.
Okay, well, let's continue over lunch then. Thank you.
Thank you.